this is Professor DePaulo. Welcome you back to Psych 220, Behavioral Statistics Fully Online. And today I'm going to be talking about Lab 3, which covers ANOVA, correlation, and regression. So in Blackboard, under the Excel Data Analysis tab, you'll see a folder for Lab 3. And Lab 3 is not really complicated. It's just there's a couple of steps you have to take to really derive at the right answer, especially since we're using Excel. And Excel, as I had mentioned throughout the course, the good thing is it's free. Everyone has it. It's not difficult to use. The bad thing about Excel is you can't do as much in Excel as you can in a devoted stats package like SPSS, SAS, R, Python, things like that, right? So we're going to do what we can in Excel. We can do some of these basic things in Excel, but it's going to take a few more steps to get it done. So I'm going to first start by opening up the Lab 3 data set, which I provided for you in Excel. And I formatted the data for you to make things a little bit easier. And we're going to test the first hypothesis, which is that there is a difference in stress level depending on degree obtained. So basically what I'm looking at here is education level, and there's five levels of education: high school, some college degree, master's degree, and PhD. And then I'm looking at the stress levels associated with each of those levels of education. And I'm hypothesizing that there's a difference in stress level depending on the degree obtained, depending on your level of education. That's the research hypothesis. The null hypothesis, of course, is that there's no difference in stress level depending on the degree obtained. And so this is kind of a tricky question to really research, because you could think about, if you have an advanced degree, you're probably going to have a more demanding job, and there's going to be a lot of stress involved. However, you could also think of it as, if you're just starting out, you don't have much experience, and you're going to be stressed at like an entry-level job. So it can kind of go both ways, but I want to just look to see overall, is there a difference? Does education play a role in terms of stress levels? And there's a lot of other things that affect stress level too, but we have to pick a starting point, and this is the starting point. So this is an omnibus test, so this is a one-way ANOVA. We have one dependent variable, which is stress, and we have one independent variable, which is education, and that independent variable has 5 levels. As I mentioned just 2 seconds ago, we have high school, some college degree, master's degree, and PhD. So the first thing we have to check when we're running ANOVA is we have to check the homogeneity of variance assumption. So we want to make sure that the variances are relatively equal. And by relatively, I mean that you don't have one variance that's like astronomically much bigger than another. And so to check this, I can eyeball the variances, but I could do a more formal check by doing an F test that we did previously for the independent groups t-test. I'm going to do that on the ANOVA, except we have 5 groups. So what I want to do is I want to look at the largest variance of the 5 groups or 5 levels, and I want to look at the smallest variance, and I want to compare them and make sure that they're not exceedingly different. So I can do this first by running descriptive stats to actually find the highest and the lowest variance. So we've done this already, so let's open the data set up. And we're going to run descriptive stats. So here's your Lab 3 data. It's under Sheet 1. Sheet 2 is basically it's kind of a legend. So it tells you basically what the data mean. So you have gender, you have marital status, you have stress levels, education levels, medication for depression, and drug use. So these are just a couple of variables that I had data lying around. And let's look at this. So let's go back, and I want to run descriptive stats first to find the highest and the lowest variance. So here are my variables I'm looking at. So it says stress high school, stress some college, stress college degree, stress master, stress PhD. right? So these are the 5 columns I'm going to be using. So let's run descriptive stats first. So we go into our data tab, and we go back to data analysis again. And we want descriptive stats. So we're just going to look, this is just to get the variances first. So we want to know which group has the highest variance and which group has the lowest variance. And then we're going to compare them. So input range, once again, I got to hit this arrow. And now I want to select the groups. So we want to select these 5 columns because they're all stress. Labels in the first row. I selected the whole column, so labels in the first row. And I want summary statistics. That's going to get me variance and a bunch of other stuff. Hit OK. So I'm just going to clean this up by double clicking on the columns to make it a little bit neater. Let's look at this. So I don't really care about the means right now. Let's look at the variances. So I want sample variance row 8. The highest variance is college degree, 47. And then master's degree is the lowest. So I want to compare college degree to master's degree. So I'm going to do that next. College degree versus master's degree. So let's run the F test. So go back to data analysis. And let's do the F test for 2 samples of variances. And I want college degree and master's degree. So variable 1 is going to be college degree. Click on the arrow. Select college degree, this column here. And then master's degree is right next to it. And labels in the first box. Hit OK. And here's my test of the variances. See, my F value is 5.27. And my probability value is 0.10. So that's not less than 0.05. I need that to be less than 0.05 to say that the variances are different. Since the p-value is greater than 0.05, we're going to fail to reject the null, and we conclude that the variances are the same. So this is the homogeneity of variance assumption. This is what I want. For this test, I want to fail to reject the null, because I want to say that the variances are the same. That's kind of the opposite of what I usually want to do. I usually want to reject the null. But for the homogeneity of variance test, I want to fail to reject the null. And that's what's happening here. I'm failing to reject the null because the p-value is greater than 0.05. And since this is the largest and the smallest variance, then there's going to be no difference between the intermediate ones, right? Because there's going to be less of a difference in variance if I look at another 2 groups. So I don't have to test all the groups. I just have to test the largest and the smallest. And there's no difference, so therefore the homogeneity of variance assumption is satisfied. The variances are not severely different that I can't run the ANOVA. So I'm happy. So now I can run my analysis of variance. So let's go back and let's run the analysis of variance now. So data analysis. We want to do ANOVA single factor, because we have 1 dependent variable, so that's going to be single factor. If you had a factorial ANOVA, you could do 2-factor, and then replication means if you have a repeated measures part of the ANOVA. And that's kind of a little bit advanced, and it's not really the best thing to run in Excel. So once you start getting into a more advanced analysis, you want to run them in R or SPSS or SAS or Systat or something like that, right? Because Excel is just the basic stuff. For a course like this, Excel is fine. But for like real professional data analysis, I wouldn't use Excel. The benefit of Excel is it's free and it's easy to use, and you need to use it anyway. It's the best software for managing data, organizing data, manipulating data, but it's not the best for analyzing it. But we can do the ANOVA here, the single factor ANOVA. Hit OK. Now our input range, we need to select the 5 columns that we're using. So let's select those 5 columns. For stress, once again, So I selected those 5 columns. I want labels in the first row. Alpha's 0.05 is good. Hit OK. Here's my ANOVA. Now, there's not much data here. You see there's only 5 people in each group. So this is very little data. Ideally, you would want to have more data than this. Ideally, really ideally, you would want to have 30 people in each group because then you guarantee to have normality, a normal distribution for each of those groups in the population. However, if the sample sizes are the same in each group, that normality assumption for ANOVA that says basically that each level of the ANOVA has to be normally distributed in the population has to be normally distributed, that is really flexible, especially with equal sample size. You can violate this to a great degree. So I'm not really concerned with the normality assumption. I know the book talks about it, but with equal sample sizes, that normality assumption is not a big deal. There's what's called a robustness of the statistic of the ANOVA to the violations of normality. The more important one is the homogeneity of variance, and we showed that that works. So I'm good moving forward with this. And let's look at the F value. Wow, the F value is gigantic. It's 86. That means there's a huge difference between the groups. The P value is really, really small. That E means is scientific notation. So it's 3.68 times 10 to the negative 10th power, which basically means you move the decimal place 10 points to the left. So you're dealing with a really tiny P value. Much, much less than 0.05. So we easily reject the null here. And now when I reject the null here, all I'm saying is that there is a difference. I'm not saying where the difference is. I'm saying that these 5 groups are not the same. That's all I'm saying when I reject the null for the F test here, the ANOVA. The 5 groups are not the same. It doesn't tell me which groups are different from which other groups. It just says they're not all the same. So that's useful to a degree, but we need to go a little bit further. So to go a little bit further, we can then follow up. So once I get a significant F value here, I want to follow this up with post hoc tests. And I had mentioned, different post hoc tests in the lecture. You have the Bonferroni correction, you have the least significance difference test, you have something called the REGWQ. These are things that you're not responsible for, obviously, and they're just a bunch of, there's like 20 of them, different post hoc tests. Some of them are more conservative, some of them are more sort of liberal in terms of rejecting the follow up the post hoc tests. Which one's the best? That's really up to the individual to decide. I, however, use the Tukey test because it's used very often. So it's used in the literature constantly, and it's also tends to be not so conservative. So I'm more able to find differences. It has higher power. It has higher statistical power than, say, the least significance difference test and the Bonferroni correction. These are very limited tests. It's almost impossible to find differences between groups running these extremely stingy tests. So I like the Tukey HSD, the Tukey honestly significance difference test. And that's what I'm going to use. Your book talks about it, so I feel more comfortable talking about it. Now, if we go back to the handout I made, basically I walked you through this already. Here's our F test, right? Now we need to do the Tukey honesty significance difference test. We need to actually do this manually, unfortunately. In Excel, there's no option for doing the post hoc tests at all. None of them. This is another limitation of Excel, is some basic things like this you can't run. So you have to kind of do it by hand. And what I mean by hand doesn't mean like take out a scrap of paper. I mean, you do it in the spreadsheet. And then you have to make a chart to compare it. So I have 5 groups here. I need to compare all these groups to each other. So I need to compare group 1 to group 2, group 1 to group 3, group 1 to group 4, group 1 to group 5, group 2 to group 3, group 2 to group 4, to group 2 to group 5. You see what I'm saying? So there's 10 post hoc tests in total that I have to run. So I have to run 10 of these Tukey tests. Now, Tukey, the HSD test gives me the minimal difference that the means have to be apart for them to be different from each other. So if your two means are different by more than what the Tukey value is, you could then say they're statistically different. Okay. To calculate the Tukey test, we need something called Q, which is the studentized range statistic, and we need the mean squares within, which we have from the ANOVA. So the mean squares within here is where it says within groups. That's the mean squares within. Here it's 25,7,333. And I need n, which is the number of participants in each group. And that in this case, the number of participants in each group is 5. So let's go back to where the Tukey is. Where the ANOVA is. So let's start manually doing the comparison. So the first thing I need to do is find the means. Well, I have the means right here. Okay. And now I need to use these means, and I need to calculate the HSD test. So the HSD test is equal to, so let me type it out here, Q times square root, let me just put Q times square root of the MSW divided by the number of subjects in each group, the N. So that's my formula here. Okay. So now I need to find Q. Q is the studentized range statistic. So in your textbook, you'll have an option to find Q. So open up your textbook in your appendix, and you'll be able to find Q. So I'm grabbing the textbook. So we flip to the back. Let's see what appendix it's in. Statistical tables, appendix B. And you got to keep flipping through the back here. And it's table B5. Table B5 in appendix B gives you a studentized range statistic. The number of groups or treatments is K, and that's on the top of the chart. And then on the side of the chart is degrees of freedom. Degrees of freedom within. Okay, so in this case, my degrees of freedom within is 15, because that's in the ANOVA right here, 15. And my degrees of freedom with actually the number of treatments, the K value is going to be 5. So I have 5 treatments, and I have 15 degrees of freedom within. So I find 5 on the top and 15 on the bottom, and I get 4.37 for 0.05, and I'm going to use 0.05 here. So 5 and 15 gives me 4.37. So Q is 4.37. So I'm going to make a note. So Q is 4.37. And now I have the rest of it, so I can just basically plug in now and solve. So let's see what we got here. So I got to start to solve this. I'm going to put an equal sign. Equal sign tells Excel to do the calculation. So now this is very easy to do in Excel. So let's do the correlation. So let's open up another sheet. Let's go back to actually the data, sheet 1, which is the data. And I'm looking at stress and income. So stress and income, what's the relationship? Go to data, go to data analysis. Really simple to do the correlate. Pick correlation, pick input range. Now, the little tricky thing about the input range is if you're doing a correlation, it's probably best to do the whole data set. And I'll show you how to do the whole data set at once. If you're just doing two columns or two variables, you got to make sure that those two variables are next to each other. If those two variables aren't next to each other, Excel gets really cranky. So if the two variables aren't next to each other, do the whole data set. And so how do you do the whole sheet? Click on this input range. Click on this little corner here. Left click this corner button here at the top. It selects the entire, see how it selects the entire data set. Every column, every value is selected now. Now this thing may blow up. Hit labels in first row. It's going to give you the whole data set. It actually won't. So it's cranky because some of the variables are shorter than others. So it won't even let me do it in this situation. So let's try the two columns. So what you need to do for the correlation is make sure the two columns you're using are right next to each other. Otherwise, Excel gets kind of cranky. And it gets cranky because some of these variables here, like I made these 5 levels, and so I split this variable up into 5 different columns. Excel doesn't like that, but you have to have that to solve the problem in Excel. So once again, Excel gets cranky. There are certain things you have to do right, otherwise it just gets angry at you. So let's make sure that the two variables we're selecting are next to each other. And that brings me back to the fact is, Excel kind of is not the optimal, but considering we can't be in class, we don't have access to SPSS, and to access it remotely all at once, it would be a disaster. So we're kind of stuck in this situation. You could use R, so R is an alternative, and it's really popular and it's free. The problem with R is there's a steep learning curve, as I mentioned many times previously. And if I were to teach the course in R, some students would be very upset. They'd be extremely frustrated. You'd need me like 24/7 to like help you with some things. So that's kind of hard. So I'm trying to keep it simple. Click this up arrow here. But if you want to know some things about R, just let me know. I'll be happy to talk to you about R. I'm just not requiring it because people would be in a mass panic. So we're going to look at stress and income. Select stress, drag across to income, make sure they're next to each other. If they're not next to each other, you could just copy and paste the column so they're next to each other. So it's very easy just to move it by copy paste. Make sure labels is checked off. Hit OK. And there's our correlation between stress and income. So obviously stress and stress is the same thing, so the correlation is 1. Same thing with income and income. So the diagonals of the matrix are always going to be 1, because if you're correlating a variable with itself, it's going to be 1. But income and stress here is 0.2124, and that's a pretty small correlation. So there's not much of a relationship between stress and income, and that's because it's a complicated relationship. Some people are really stressed, they have low-income jobs, or they're working multiple jobs, and they're financially strapped, and they're going to be stressful. Other people are working, are CEOs of companies, and they're making tons of money, but they're also stressed because they have a million responsibilities, and they're managing so many different people. So there's not really a good relationship between stress and income, because it can be multiple versions of stress. You have financial stress, overwork stress, versus I have a ton of responsibility stress. Different kinds of stress. So there really is a weak correlation here. If I square this, I get R squared, which is the percent or proportion of variance accounted for. So if I square 0.12, I get about 14% of the variability. So 14% of stress is accounted, or income is accounted for by stress, whatever way you want to go. 14% of income is accounted for by stress, or 14% of stress is accounted for by income. That's pretty low. That's 14%. Where's the other 86%? That's not explained here. So there's a lot more you need to look at in terms of trying to figure out what contributes to stress and income. There's more variables in play. So that's really easy to do a correlation. Now, if I'm doing a regression, it's a little bit different. So if I'm doing the regression, I'm going to predict depression by using income. So I'm going to predict depression, and I'm going to use income. So depression is my Y, income is my X. So the difference between correlation and regression is that correlation just looks to see if the variables go together. Do they vary together? Are they associated? Whereas regression gives you a prediction. So it tells you which direction to look in. So X is always predicting Y. So I'm always looking from X to Y. I'm not looking from Y to X. Whereas in correlation, I'm looking at X to Y and Y to X. I'm looking both ways. And there's also room for other variables as well to contribute to the relationship. With regression, I'm giving you a direction to look at. I'm saying start with X and use X to predict Y. In this case, X is going to be income and Y is going to be depression. So I'm predicting depression using income. So how much money do you make? Does that contribute to your level of depression? It seems like, if you make more money, you should be less depressed, right? But that's not necessarily the case, because some people, they have all the money in the world and they're constantly unhappy. Other people don't have much money and they make the best of the situation and they're happy because they have other things. So it's not just, income leads to depression. It's a complicated relationship. Like many things in psychology, there's a lot going on here, which makes psychology both interesting to do research in and also incredibly frustrating at the same time, because there's so much. People are very complex. So very rarely would you see one variable predicting here. Now, could I run many variables predicting depression? And income could be one variable. Yes. If I ran 5 predictors, and income is one predictor, and there's 4 other predictors, could be health, could be another predictor of depression, could be social support, friends, family, could be the way you view the world. There's a lot of different variables that can predict depression other than income. And if I keep adding variables, I get a better model. I get a better prediction. So could I do that? Of course. I could run what's called multiple regression, where I have many predictors and I have one dependent variable. And when I do my analyses, I usually run many predictors. I even run interactions of predictors. So where you have like an interaction effect among two predictors. That there's an X and there's a Y, and there's an X times, there's a X1 and an X2, and there's an X1 times X2 as a predictor. There's an interaction term, like you have in ANOVA. Could you do that? Of course. You can make these things very complicated, but for this class, we're going to stick with one predictor and one criterion or dependent variable. And let's look at it. So let's look at income leading to depression. Let's go back to our data set. Sheet 1, I want income leading to depression. So data analysis. Let's do income. So let's find a regression first. I see correlation here. I got to go down here for regression. Now the Y variable, that's what I'm predicting. I'm predicting depression. So let's find depression. Now for this selection, do not just select the entire column, because Excel will be cranky and it will just blow up and say error. You need to only select the data and the label. You cannot select just the entire column, because there's a lot of blank cells in the column, and for some reason Excel gets pissed when you select blank cells for the regression. So I'm going to left click on depression and drag down. Don't select the entire column this time. Just drag down like that to the end. And do the same thing with our predictor. Our X is going to be income. So click on this, find income, drag down. The reason I know this is I did it the other way. I selected the entire column and Excel just got really angry at me and kept saying, "What are you doing?" in some cryptic language it uses. And it wouldn't allow me to go on. So since I selected the label, click the box labels. I always like to select the label for some reason, just it's easier if I do it consistently that way. Leave the rest of this unchecked. Then for residuals, you want to check off residual, standardized residual, and check off the line fit plot. This is going to give me the scatter plot with the line. And then hit OK. And here's my regression. So I'm just double clicking on the columns, between the columns to like space it out so I can read the whole thing. Because it's kind of smushed together, so I just double click to space it out. This is my my R. This is in when I have one predictor and only one predictor, this is the same as the correlation. So the correlation is 0.52. It says multiple R. The reason it says multiple R is because you can have more than one predictor. And if I have more than one predictor, it's going to give me what's called the multiple correlation coefficient, which is the correlation among 3 or more variables. We are not doing that in this class, but in this case, when we have 2 variables, multiple R is the same as Pearson R, the little r. So big R is the same as little r here. It's 0.52, the correlation. If I square 0.52, I get R squared, 0.276. And that means that the model, the regression model here, accounts for 27.6% of the variance. So the predictors, in this case income, accounts for 27.6% of the variability in depression. That's not bad for one variable. That's a pretty strong finding. Income does play a huge role in depression. That's what I'm seeing here. There's still 73% of the variance that's not accounted for. So that basically means that there's a lot more to depression than just income. But still, income's only one predictor and it's accounting for 27.6% of the variability, which is really high. That's a real positive finding. Adjusted R squared is the R squared in the population. So the R squared is the sample value. The adjusted R squared is the R squared you find in the population. They should be relatively similar. However, if you have a huge sample size, then your adjusted R squared could be significantly less than your sample R squared. See, the adjusted R squared is adjusted based on the sample size. It's the population parameter. You don't need to know that for the course, but that's something that comes up in more advanced analysis. Standard error we talked about in the lecture. It's the basically standard residual, the standard error of the residual in terms of the prediction error. Or technically it's the standard deviation of the residual, which is the prediction error. Observations is 25. So there's 25 data points, which is a really small sample. You would want more than this. The model as a whole, the regression model as a whole has an F value of 8.79 and the significance value of 0.006. That's less than 0.05, so we say that the regression is significant. What does that mean? That means that the predictors, in this case income, predicts more than 0% of the variability. Wow, that doesn't say much, right? It just says that basically the predictor is predicting more than 0% of the variability in depression. If this value is not significant, then your model is useless. So this is going to be significant most of the time. If I add more variables, this is going to drive the significance down. It doesn't mean much. It just means it's not 0. The same with correlation. If you test the significance of a correlation, all it means is it's not 0. It doesn't tell you anything other than that. So this just tells me that the regression is not 0. good. Doesn't mean it's a good regression. In this case, I think it's a pretty decent regression, to be honest with you. But just because it's significant doesn't mean it's a good regression. It just tells you it's not zero. Another way of looking at this is that the slope is not zero. The slope of the regression line. So this tells me the slope of the regression line is not zero. It's not a horizontal line. Or yet another way of interpreting it is that the regression model is better than using the mean of y as a predictor, which would be a horizontal line for the slope of zero. The regression model is better than using the mean of y as a predictor. If the regression is not significant, then the mean of the dependent variable becomes the best predictor. So the line becomes horizontal. Slope of a horizontal line is zero. Once again, it's not that important, but you got to have this. If you don't have this, you just junk it. It's over, right? There's no point even looking at anything else. So now that I have a significant model, I can then interpret it. Now, what you need to interpret is the coefficients. You have the y-intercept, which is called intercept, and you have income, which is the predictor. This coefficient 73 is the y-intercept. The coefficient below it for income is the slope of the line. Since there's only one predictor, there's only one slope. And the slope of that one line is negative 0.35. So there's a negative relationship here. There's a negative relationship between income and depression. So how do we write the line? Well, the line is y hat. It's hard to do y hat on here, but y hat. Predicted y equals. Now we have to have remember the formula is bx plus a. That's the formula for the line. You used to learn in algebra mx plus b. It's the same thing, we just changed the characters. In statistics, we call b the slope and a the y-intercept. So b is the slope, a is the y-intercept, y hat or y prime, whatever symbol you want to use. I think the book uses y hat, is the predicted value of y. I can't write y hat in this thing. I'm sure there's a way to do it. I'm not going to waste 10 minutes looking for it. So it's y, this is the predicted value of y. So this is y hat. So for this equation, it's going to be y hat equals the slope, negative 0.353, I'll leave it like that, times x, right? So that's the slope, times x, plus y. And y is going to be the y, plus the y-intercept, I'm sorry, plus a. So the y-intercept is 73.947. And there's your regression line. And I have that all written down here. So here's the hat. I actually wrote the hat on the Word document. So negative 3, if you want to look at what the hat, this is what it looks like with the y hat. Here's the equation actually. Negative 0.353x plus 73.947. Now if I want to predict the value, let's predict for 20. That's what I gave on the sheet here. So if I want to predict a y value, so if I want to predict depression for an income of 20,000, I can plug 20,000. Income is given in thousands, so I just need to put 20 in. 20 represents 20,000 in for x. So y equals negative 0.353 times 20 plus 73.947, right? And let's just do that quick. Times, our x is going to be 20 plus 73.947. And when I do that, I get 66.887. So if you're asked to predict a score, all you do is plug in the predicted value for X and then solve it. And so for someone that makes 20,000 in income, their depression level is going to be 66.887. So the predicted values are on the line. So these values are on the line, and the actual values are on the scatter plot, right? So let's see what that looks like. Here's our scatter plot. Now what I can do is I can make this a little neater. So these orange dots here represent the line, the regression line. The blue dots represent the actual scores on depression for each person, for the 25 people. And if I just put my mouse over it, it tells me the value. So let's go back here. I want to right click one of these orange dots, and then it gives me an option to do outline up here. So if I click on outline and I go down here, it's going to give me weight of the line, and I can pick the weight of the line to make up the regression line. So let's make it like that. I'll use 1.5. 2.5 is thicker. I'm going to use 1.5. And now the line is in there. So I connected the orange dots onto a line because I want a line. I just don't want a bunch of orange dots. But for some reason, it gives me a line when I do it this way. I think there's a way to do it through the graph menu that you won't have this problem. But when you ask for this through the data analysis menu, it doesn't give you the line. It just gives you those orange squares, and you just want to connect them to the line. Now, if you don't like the fact that the orange squares are a different color than the black line, well, we can change that too. So we can actually go find chart design up here on the top. If you click on chart design, it gives you like a whole bunch of different options. And you see now the line is colored as orange. So that makes you happier because now everything's the same color. This one's nice. I like that one. This is the one. This one I like. Don't like that one. I like this one. This is the one I kind of like the best. So now there's your graph. Here's your regression line that we just found. Here are your scores. You can see most of the scores are around the line. That shows you that the regression is pretty good, that the actual scores are clustered around that line. So you're looking at those blue scores clustered around the orange line. I wish there was a way to hide these dots. I don't think there is. There probably is a way to hide the dots, but I'm not going to be able to figure that out by now. So these are the vertical distance between each dot and the line is the residual. And you see most of these are close, so most of the residuals are small. Here's one that's pretty, out there. This person scored 25 for income, but they scored 100 on the depression. That's a lot. So this person really, they didn't make much money, but they had a huge amount of depression. More than expected, more than everybody else. So they could be an outlier. This 25, 100 could be an outlier. This person here could be an outlier. This person scored 56 for income, 56,000, but their depression level was 6. And so they should be, according to the line, all the way up here. Here's the line. Here's their value. So they're really far from the line. They're even farther than this point. So these 2 points are the possible candidates for outliers. And yes, you can have outliers. These points don't fit with the line. And the outliers can influence the line. That means they can pull the line in different directions. So this guy up here pulls this line upwards towards this point. Technically, the term for this is called leverage. And the further this is from the line, the more leverage it has. that basically means that it has an influence on the line, the regression line. This guy down here, or girl, or whoever, pulls the line in this direction, so it pulls the line down. So the fact that they're on opposite sides of the line kind of counteracts their effects, right? But if you had this person up here, if this person was down here, that would have more of an influence on the line. The line would then be pulled downwards. But since they're on opposite sides and they're almost the same distance from the line, they probably cancel each other out a bit. But it's important to notice this in terms of, like, do you have an outlier here? What's going on with this person? You know, why are they so less depressed? I mean, you know, you have people here making a lot more money. This person here is making 154,000. Their depression is pretty low, but the depression is much higher than this person, and this person is making 1/3 of their salary. So what's going on? Why is this person strange in some way? Atypical of the general population? We only have 25 people, so to have one person or two people that are outliers can really alter the results. So you want to investigate this. First, is it an outlier? And if it's an outlier, then you need to go research it. You don't just remove it. You just don't say, oh, it's an outlier, let's get rid of it. You got to, you got to go research it. Figure out what's going on. It could be a data entry error, it could be something else. So let's look at the residuals. These are the actual residuals for each data point. These are the standardized residuals. So these are the z-scores. Remember with z-scores, when we found outliers, we wanted z-scores that were greater than 2.58, right? So we wanted something greater than 2.58, and we wanted or something that's less than negative 2.58. So those were our criteria for the outliers, greater than 2.58 and less than negative 2.58. So let's look at those z-scores here. Just skimming at this because there's not much data, we can skim it. Anything that sticks out to you? This one. This person had a huge difference, huge residual. And they were 3 standard deviations below the mean. So if they're below the mean, below what they're expected, they have to be on the bottom part of the line, right? So that's this person, the bottom. So it's negative, so it has to be below the line. That's this person right here. This person is an outlier. So I need to go research. This person's not. This person's at 2 point something in terms of their z-score, standardized residual. This person's at -3 standardized residual, which is the z-score. So go look into what's going on here. You know, is this a data entry error? That's the first thing that comes to mind. Did you make a typo when you entered the data? And this is not a real point. Or is this person just really strange? And if they're really strange, is there a reason for them being really strange? One common reason for them being really strange is they weren't taking the test seriously. They didn't answer seriously. So now go back and look at their responses to other questions. You know, I've had it plenty of times. You give a survey, because a lot of this regression stuff is based off of survey data. You give a survey and people are just like, you know, they just circle anything. Or they're not paying attention to the questions at all. They're just answering randomly. And that's not good. So if you go back and you find that this person is not, you know, paying attention and their answers are just really all over the place and nonsensical, and you can tell that they're just not reading or taking the test seriously or actually reading the questions, then you can make an effort to exclude their data. So you have to do a little bit of investigation here. But if you think that their answers are normal, they took the task seriously, they're just different from everybody else, then you have to leave them. So the outlier investigation is mainly to see if there's a data entry error, typo, or there's a problem with the person taking the task seriously. They skipped a bunch of questions. They answered the same answer for every question on, what's called a response set. There's some systematic bias there that can justify removing the person from the study. If they're just, an oddball, you have to leave them in. You can't just get rid of them. You can't say, well, they're weird, so let's throw them out. It doesn't work that way. But it's important to investigate these outliers to make sure that they're legit. This person just could be a really happy person. Maybe their life is good. They got other things going. So it's not just about the money. It's about, you know, their life is really good. They're really positive people. They could be very spiritual. They could be madly in love. They could be happy to be alive. You know, whereas everybody else is kind of like, I'm struggling. Here you get these people saying, I'm making no money. I feel miserable. I can't afford anything. Can't live like this. Right? And this person's like, yeah, I'm pretty comfortable. There's no real reason for me. My life's not perfect, but I'm pretty comfortable. So it makes sense in terms of the relationship that if you have more money, you're probably not as depressed. And, mental illness goes with, lower socioeconomic status. And people that are really feeling it are up here. This person's kind of in the middle. And they should be somewhat depressed, not super depressed, but somewhat depressed. They should be up here somewhere, and they're way down here. They're just kind of like, yeah, doesn't bother me at all. I feel great. So, gotta investigate those people further. You gotta investigate people that are not absolutely miserable. Figure out, why are you happy? Happiness is an illness. No, I'm just joking. But they're obviously taking things in stride pretty well, maybe too well. Who knows? But that's basically how you diagnose this stuff. Uh, and that's it. And then you have all this input. And so what you want to do is you want to copy the output into a Word file. Just copy and paste all this stuff into a Word document, and then save that Word document as a PDF. And if I ask you, is there a significance difference, you're going to answer me yes, and then write out, show me the data. Just don't print out. What happened last time is people just printed out the data and they said, here's the printout. They didn't put anything else. They said, is there a relationship here? Or they just gave me the charts. Yeah, the charts are good, but you need to tell me, is there a significant difference? Tell me why. Point me to the F value. Point me to the P value, significance value. Point me to the regression. Give me more detail than just a printout of the analysis, because the printout doesn't, it's kind of like magic box, right? You get this printout and you're like, what do I do with this? So give me more detail and answer the question. So I gave you a bunch of tasks here. Do not print out the entire data file with all these, scores. Some people were sending me PDFs that had 80 pages, and I had to scroll through 70 pages worth of data, just raw scores, to get to the actual answer. So, so is there a significance difference? Oh, my scatter plot got messed up. I gotta go fix that. So these are your questions that you have to do. Is there a difference in income across levels of education? So yes or no, run the ANOVA, check the homogeneity variance assumption, then test the hypothesis, then calculate the two key post hoc tests if it's significant. And then 2, calculate the correlation between anxiety and depression. Is it weak, moderate, strong? Tell me what you think. And calculate the regression equation predicting anxiety from income. What's the equation of the line? Predict one's anxiety level if they have an income of 50. And are there any outliers? So all the stuff I just went through with the different variables in here, pretty basic. I'm going to fix this scatter plot for you because when I copied it over, all the dots went all over the place. So I'll fix that. And that's it. And I think I just went through basically everything you have to do. And hopefully that's helpful. And if you have any questions, let me know, either through email or sign up for my office hours. You could just drop in. The link is posted to Blackboard. But I'd rather you sign up because I have tons and tons of advising. It kind of died down for a bit, but now people are in mass panic about getting advised because the end of the semester is coming. If you haven't been advised, if you haven't registered for next semester, please register. If you need help with that, let me know. Reach out to me. I could do advising with you. through Zoom, through whatever. Get it done so we can get you registered for next semester. Because don't just wait to the very end. Let me know though if you have a problem. So either way, if you have a problem through email or through Zoom, let me know. I'll be happy to help. Hopefully that helps you, and